Hi folks, welcome to the last part of the first Unit 5 lesson. Okay, so we're going to take a look at this question here that I asked you to think about. It says, how can you create a vector with the same direction as vector v, but with a magnitude of 1? Okay, so when you're trying to determine a reasoning for something, good idea to work with a particular value. Okay, so let's say I take some vector and I say, well, here it's got magnitude 5 and there's its direction. So I want to create a vector that's in the same direction, but with magnitude 1. So since I'm essentially creating a parallel vector, I know I'm going to be using scalar multiplication. Okay, so if I'm looking for, so if this is vector v here, and I'm looking to essentially have a vector that's 1/5 the size of the original vector, well, this is just going to be equal to 1/5 of my vector v. Okay, so positive scalar multiple, so same direction, and the magnitude of the new vector is just, remember what we said, k, or the absolute value of k, so 1/5 times the magnitude of the original vector, which is 5. Okay, so 1/5 of 5 is 1. Okay, remember how we defined scalar multiplication. It has a magnitude of k times, so in this case here, 1/5 times the magnitude of vector v, which in this case here is 5. 1/5 of 5 is 1. Okay, pick any other vector. Say this has a vector of 30, and I want a vector of length 1 exactly in the same direction as the original vector. Well, what am I going to have to do? I'm going to take the original vector, so say this is w, take the original vector w, okay, and I need to create a vector that has length 1. So I'm going to take the magnitude and again multiply it by 1 over that magnitude, or divide it by the magnitude of the original vector. And this now gives us a way to determine a vector that's the same direction but with magnitude of 1. And this is what we call a unit vector. Okay, so unit vector means a vector with magnitude of 1. Okay, and it has its own symbol. We're going to see that unit vectors are going to be extremely important for us later on, so we give them their own symbol. So normally we use an arrow to represent a vector. If it's a unit vector, we use a little hat. Okay, so this represents a vector with magnitude of 1, so that means that the magnitude of this unit vector is always going to be equal to 1. Okay, so if I want to create a unit vector in the same direction as v, well, I'm going to take my original vector v and I'm going to multiply it by 1 over its magnitude. Okay, so if the magnitude is 7 and I multiply the vector by 1 over 7, well, the new magnitude is always going to be equal to 1. So we can write it in this way, which is more indicative of the fact that it's a scalar multiplication, but often we just write it like a division. Okay, so we say the vector v divided by its magnitude. Okay, but in the end, it's actually equivalent to taking the vector v and multiplying by the reciprocal of the magnitude. All right, and if we apply our representation for the relationship between the magnitude of a scalar multiple and the original one, well, let's take the magnitude of 1 over v times v, and let's apply our formula here. So it's the absolute value of 1 over the magnitude of v times the magnitude of v. So since that's a number, this is an absolute value, just to recall. In this case here, this is a magnitude. Okay, well, 1 over the magnitude of v is already positive. So if I take the absolute value of a positive number, it just stays exactly the same. Okay, and I multiply that to the magnitude of v, which is now a number, we see that they just cancel out to 1. Okay, so keep this in mind because this is going to be very useful for us in a little bit a way to take any vector and create a unit vector in the same direction. Okay, so the last thing we're going to look at is this idea of considering one-dimensional vectors. Okay, so if you think of how we define vectors, it was this need to be able to work in 2 dimensions. Okay, so say I use the arrow, say this represents an arrow, tail to tip. Okay, it allows me to represent any direction with any magnitude on the 2D plane. Okay, I can also take this and move it up into 3D. So going upwards or maybe going downwards. Okay, I can use this arrow to represent any motion in 3 dimensions. Okay, or any position in 3 dimensions. Well, ideally, if I'm doing something in 2 dimensions and 3 dimensions, well, it should also work in 1 dimension. So can we think of the number line and moving just back and forth in terms of this idea of vectors? And yes, we can, because here, what does this represent? It represents the vector in the positive direction, okay, with magnitude of 10. We used to describe this as the number 10. Okay, this would just represent the vector going in the negative direction with a magnitude of 10, which we used to describe with negative 10. So this idea of direction, we could get away with just using the concept of positive and negative to describe direction. So there's an urban legend that says, some grade school teacher taught all of arithmetic using vectors. Okay, so they didn't talk about the number 3, they talked about the vector 3. Okay, and then this would have been the vector, opposite vector, so the vector negative 3. Okay, and when they wanted to find something 2 times the vector 3, well, they did scalar multiplication. 2 times the vector 3 would be this here. The vector 6 was 2 times the vector of 3. Okay, negative 3 times the vector 3 would have been the vector negative 9. Okay, now the reason why it's going to be interesting to think of these one-dimensional vectors is because at some point we're going to want to consider other operations with vectors. Okay, we talked about multiplying a vector by a scalar quantity, but at some point it makes sense that we're going to want to be adding vectors together. So example, if I'm applying a force on an object but in 2 directions, I'm going to have to find a way to combine these forces. I'm going to have to find a way to add the forces together. So we're going to have to talk about adding vectors together. And what we're going to see is we're going to use this idea of thinking of vectors in 1 dimension as inspiration for how we're going to define these other operations that we're going to need with vectors. Okay, so you can already maybe start to think, how would I add together the vectors 2 and the vector 3? Now we know what the result, or what we want the result to turn out to be. How can I accomplish this? Okay, so something to think about, and this is where we're going to start things off in lesson 2. Okay, that's it for lesson 1.